In this lesson, we're going to talk a little bit about rates of reaction. So we can first start by trying to define what we mean when we talk about a rate of reaction, right? So when we talk about a rate of reaction, we simply mean that it is the change in either the concentration of the products, so products per unit time, or the change in concentration of our reactants also per unit time, right? And there are many factors that actually affect the rate at which a reaction proceeds, and we're going to talk about all of them. So this rate over here is actually measured in mole per cubic decimeters per second. So that is your let me try to find another marker. Okay, and there are actually many factors that affect the rate of a chemical reaction. The first one is the nature of the reacting substances. So, what are the reacting substances? Is it oxygen to hydrogen? Is it iron to sulfur? That will definitely affect the rate at which a certain reaction proceeds. If you think about it, the surface area, the concentration, the temperature, as well as the presence of a catalyst. And in this lesson, we're going to try to discuss all of them, and you will see how they actually affect the rate at which a reaction proceeds, right? And we're going to explain this using something that is called the collusion theory. And according to the collusion theory, um, the collusion theory is basically how I would define it. I would say it's a model that explains reaction rate as a result of particles colliding with each other. It is based on the assumption that for a reaction to occur, particles have to be colliding with each other. But not all particles essentially have enough energy to collide. Only particles, and you'll see later in the lesson, only particles that have a sufficient energy. So they must have sufficient energy. This means they're remember because they are colliding, they are moving. So we're talking about kinetic energy. This means that their kinetic energy, EK, must be greater or equals to their activation energy. And we've already defined what an activation energy is in the last lesson. So if that the kinetic energy of these colliding particles is greater than their activation energy, which is the minimum energy required for a reaction to proceed, then we will have a reaction. Otherwise, we would not have a reaction. That is the assumption of the collusion theory. Another thing that I'm not going to dwell on that it talks about is that this colliding particles must have correct orientations. So if they not correctly oriented, then we're not going to have effective collusions. So just keep in mind they must have sufficient energy according to the collusion theory, and also they must have the correct orientation so that we can have effective collusions. If we have effective collusions, it means that the rate at which our reaction proceeds will somewhat increase, right? Okay, so we're gonna use also to explain this. I'm gonna draw graphs. They are called what is it, Maxwell Boltzmann, is it Maxwell Boltzmann distribution graphs, so that I can explain how different factors such as temperature, concentration, as well, what else did I mention, pressure, actually affect the rate of a reaction. So this is what a Maxwell-Boltzmann distribution graph would look like. It basically shows the distribution of your kinetic energy. So this is increasing kinetic energy to your right? And then so it shows the distribution of the kinetic energy of the molecules. So the area under the graph is basically your particles, right? So on your y-axis you have the number of particles that are involved in that. And on this graph again, the one thing that I want you to note is this line here that actually shows our activation energy. So this is activation, EA, activation energy. So this is the minimum energy that these particles that are colliding will need to overcome in order to partake in a reaction to form products. So what are you noting? That only particles to this side of your what is it to the side of your this line of your kind of your activation energy actually have sufficient, only these particles over here where I've drawn the diagonal lines actually have enough energy to partake in a in a in a reaction to form products. These particles from here don't have sufficient energy to be involved, so they are not colliding at their kinetic the kinetic energy of their collusion is not enough for them to actually partake in a reaction. But of course, this is just according to collusion theory. So a number of things can actually change how this graph looks. So the temperature can affect how it, if we increase the temperature, you'll see how it differs. If we increase, what is it, the concentration, if we also perhaps increase the pressure, or maybe we add a catalyst, so this graph will somehow change, and you'll see how we can do that just now. So let us say, for an example, you increased the temperature, so we still have the number of particles, we still have our kinetic energy on this, on your x-axis. So this is at low temperatures. This is what this graph looks like. Look at it. And only these particles here from below your graph have enough energy. These are the only particles that are colliding or have enough collusion, what am I saying, have enough kinetic energy through their collusions. And only these particles will actually be involved in your reaction to form a product. But now we say, okay, let's see what happens if we increase the temperature. If we increase the temperature, this is what happens. We get a graph, our graph changes in this way. And now what are you noticing? That there we have more particles now from this point to this point under the graph. This means now more particles are actually colliding. So if more particles are colliding, it means that more particles have sufficient kinetic energy to overcome our activation energy, and as a result we have more effective collusions, and as a result again the reaction rate is increased. I hope that is making sense. At low temperature, we have less particles with enough energy to overcome this activation energy. There's less collusions, right? As we increase the temperature, now we have more particles. So you look at the area under your graph from here. So now we have all of these particles that are colliding with each other. They are oriented in the right way, they have sufficient energy, and as a result the rate of a reaction is increased. This is telling us that we can actually increase the rate of a reaction by perhaps increasing the temperature, right? Cool. The second thing we can change is the concentration. So let's say for a reaction where we have maybe the concentration is like 0.5 molars. So a molar is the same as your mole per cubic decimeters, the same thing. So you have 0.5 molars, that's your concentration. And you see, look at the area under the graph. Only these particles here have enough energy to overcome, have enough kinetic energy to overcome this activation energy. So there is less collusions taking place, right? The moment we increase our concentration, look what happens. Our graph now changes. And if you look to the right of your EA line or activation energy line, you realize that now we have all of these particles under the area of this graph colliding. As a result, there are more effective collusion, meaning that the rate of our reaction is increased. The last thing, or not the last thing, I'm lying. The other thing we can look at is that what happens if we add a catalyst? So what is a catalyst? So remember in our last lesson, we mentioned that a catalyst is a substance that increases the rate of a chemical reaction, right? How does it do this? It does this by lowering the activation energy. So our graph, this is what our graph looked like. Initially, we found no catalyst, and our EA, our activation energy, was at this energy here, right? Because this is increasing energy, so it was a higher activation energy, and only these few particles had enough energy and were oriented in the right way to partake in a chemical reaction. Now we add a catalyst. When we add a catalyst, this activation energy is lowered from this point to this point, and as a result now we have a whole lot of particles colliding with each other, and meaning that more particles have sufficient kinetic energy to overcome the activation energy. They are more effective collusions. As a result, the rate of a reaction is increased. So if you want another way you would actually increase the rate of a reaction would be to include a catalyst. So the interesting thing about a catalyst is that it is, you put it when you react in substances, you add a catalyst, but then it actually doesn't take it let me try to rephrase this. So you let's say you have a two reactants that you are reacting with each other and you wanted to speed up the reaction rate. You add a catalyst. A catalyst is actually not going to be used, it's not going to undergo a chemical change in the reaction itself, so it just speeds up the reaction without it actually undergoing any permanent changes. Because remember, when we have a reaction, maybe you have certain reactants that form now change into C plus D. But a catalyst will still be a catalyst, is not going to undergo any permanent change, right? So the other things that we can talk about, and without having to draw graphs, is that the nature of the reactants that are involved will also change the rate of your reactants. The other thing also that is important, let me put this here, is something called surface area. So if let's say you had iron that was in powder form, and then you also had iron that was like a chunk of a solid. So you would notice that the rate of reaction of the iron that is in powder form is actually faster than the rate of a reaction of iron that is in a solid or a chunk form. Right? Why? Because with powder forms, when your things are grounded, it means that we have more particles that are actually exposed on the surface, so it has a greater surface area. But if you have a chunk, most of those, only a limited number of particles are actually on the outside. Most of them are actually inside, so only a few of them are actually on the surface. So the surface area of this chunk would actually be reduced. So think about a typical tablet. If you have grandpa, right, and then you have tablets, you also have powder, right? This one, the speed at which the powder form of grandpa would work would be faster than the speed at which this one, which is, what is it, which is like a solid or a chunk, will work, right? Because of the greater surface area. So yeah, this brings us to the end of this lesson.